So let's make a start. What I'm going to do first, this is what's covering Fourier transforms, talk about derivation, how you obtain it, and the properties, and then unit impulse and convolution. We'll probably talk about that, if not next week, but the week after. I'm not sure yet. Depends on how we get on today. And it's tough, like I said. Chapter 3, we talked about specific non-periodic and periodic forcing functions. Okay. What about other functions? Well, we looked at other functions, other periodic functions, in Chapter 4, using Fourier series. Okay. Very complicated Fourier analysis. And Fourier series is a form of Fourier analysis, but here we're going to be talking about Fourier transforms. So let's go over because the derivation is based on the complex form of Fourier series. We'll go through the derivation again. We did do it some time ago, okay, but it's quite useful to know how this works. And so we had Fourier series in terms of a bunch of sines and cosines, okay, and a constant term. But there is a more concise way of writing that, and that uses complex numbers. Now, way back in Chapter 2, in the first lecture, we derived Euler's relationship there. E to the j theta is cosine of theta plus j sine of theta, okay? And that shows that if you take the real part of this equation, you get a sinusoid, you get a cosine signal. Okay, so the real part of that e to the j theta is a oscillation. And that was the principle we used throughout Chapter 2 and beyond. Okay? But this is a full collection of Euler's relationships. So if you have e to the minus j theta, you get a minus sign between the two. And obviously, if you've got this relationship and this relationship, you can define cosine of theta and sine of theta in terms of exponentials as well. And that's what we're going to use. Because this is what's in the sum of that Fourier series, isn't it? Yeah? You have a sum sign out here, possibly a constant term, and that equals your function. Now, obviously, we've got a relationship. So we've got an equation, an expression, that represents cosine and sine in terms of exponentials. So we can rewrite this equation in terms of exponentials. Let's do that. So there's the bit for cosine, and there's the bit for sine, and that's on the previous slide. If we go back, there's those expressions. Okay, this is multiplied by bn, and this is multiplied by an. Okay, you stick them in there, and instead of theta, we've got n theta. Okay, so that's why we've got jn theta on top. So there's our two expressions. Now what we can do is we can group these together. If we group in the e to the jn theta terms, so that one and that one, and the e to the minus jn theta terms, you get an alternative expression. Knowing that 1 over j equals minus j, because if you multiply the top and bottom by j, you get j over j squared. J squared we all know is minus 1. So 1 over j is equal to minus j. Nice little trick. And you end up with two equations. One is the complex conjugate of the other. Okay, you can see that we've got a plus here, a minus here, and a plus here. Obviously we've got a e to the j and theta here and e to the minus j and theta there. So we define two constants. Here we've got Cn, and the complex conjugate, C star n, it's the same thing, but there's a plus there instead of a minus. So we've got this bit here is Cn, and this bit here is C star n. Okay, and obviously you've got the two exponentials there. So we can rewrite that sum, that bit in the sum, as this term here. Okay? Those two things are equal to each other. So you can stick a sum in here, have a constant term, and you've got the Fourier series in that respect. We have to work out yet what Cn is equal to. So we could write that like this. So there's our Fourier series, okay, in a slightly different form. Instead of the trigonometric form, we've got it in terms of exponentials. Okay, so that's one way of writing it. But there's an even more there's a nicer way of writing this again, and this is the form that we'll use. If we take a naught over 2, which is that constant term, make that equal to c naught, which is consistent, since b naught is always 0, okay? A naught over 2 is c naught. For the second one, the star term, c star n is e to the minus jn omega t. I've replaced the theta with omega t just for the sake of clarity. Okay, and if you write that out in long form, you get this sort of expression here. C1 star, e to the minus j omega t, C2 star, e to the minus 2 j omega t, and so on. And what you could actually write, if we define c to the minus n to be c star n, you've got this, that's what c star n was, okay? C to the minus 1, well that means that if n is minus 1, you've got a minus sign up here, okay? Hence the minus sign there, c minus 2, minus 2, minus 3, and so on. And if you took the, if you work that out in terms of the sum, you get this term, which is Cn e to the j n omega t, which was the other complex conjugate of the c star n. So if we go back, if we go forwards, there's your c naught. This is the first term, which we leave the same, okay? And this is the second term, which is exactly the same as this term, by making that little trick of doing it c to the minus n. And that goes from minus 1 to minus infinity. And so you can group all those three things together, and you get a sum from minus infinity to positive infinity of Cn e to the j n omega t. Okay, it's a bit complicated, and you can go through the details in the notes, but that's the concise form of a Fourier series. So this is the one you've seen before in terms of cosines and sines, and this is the one in terms of exponentials. Okay, and this is what we're going to be using in terms of deriving Fourier transforms. What's Cn? Well, we can work that out. Okay, complex Fourier coefficients can be obtained using equations for calculating an and bn in the case where the period t is known. So this is the case where the period t is known. For c naught, okay, it is simply the integral between half periods of the function. Okay, so if you know the function, you can work out c naught, and that's exactly the same as what we had for a naught. Okay. For n equals 1, 2, 3, and so on, well, there's one half of that complex conjugate. You can separate this out, okay, and you get this sort of form, and you can make the substitution between this, and you end up getting that term there, okay. So an and bn, we know what the solution is for an and bn because we found them back in chapter 4. Okay, so I've substituted in those integrals into there, and you can see that this thing, Euler's relationship, equals this thing. So you take the integral of the function times by e to the minus j n omega t. Okay, that is Cn. And for the same range of n, so n to the minus 1, okay, you get the same sort of thing going on, and the only difference is you get minus jn omega t there. Oh, sorry, positive. Okay. And the last expression is equivalent to stating that n equals minus 1, minus 2, minus 3, and so on. And so this one is for n equals 1, 2, 3, 4, and 5, and so on. Okay. This one is for n equals 1, 2, 3, 4, and 5. But by sticking a minus sign in there, you can actually do it for n equals plus or minus 1, plus or minus 2, and so on. So for every n value. This is C of n. And that goes into that equation, the complex conjugate form. So to summarize, we've got this. Our function in terms of time is the sum of Cn, e, j, and n omega t, where Cn is this expression for n equals plus or minus 1, 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Right, Fourier transforms. As we know, Fourier series allows us to represent periodic functions. The Fourier transform allows for an alternative representation in the frequency domain of a non-periodic function. Okay. So, if we go and take what we've just discovered, f of t, this is I've I've put a subscript t because we're talking about a periodic function here. Okay, this is going to be the difference. We've just come up with this expression. And omega naught here is equal to 2 pi divided by t. As we discussed, as t goes to infinity, omega naught, or delta omega, the difference between the two omega, if you think about the frequency spectrum, you've got these points, the discrete signals, that goes to 0. So the frequency representation contains all frequency harmonics, as we talked about. Those discrete points, okay, at certain values of a of n and b of n, they become a line, a continuous line, okay? Because the difference between those signals is so small that you can actually draw the thing as a line. That was the value for C, that was the equation for C of n that we had. And so what we can do is we can take this integral, this term here, and stick it into that equation. So that's what we do. There it is. So we've taken that integral, we've stuck it into this equation, we've changed the 1 over tau to be omega naught divided by 2 pi, okay, for the sake of argument. And so you can see we've got an integral of some function times by an exponential, times by an exponential out here, and you sum it between minus infinity and positive infinity. This is where it gets a little bit tricky, and you're just going to have to believe me when I do it. Like I said, as t goes to infinity, omega naught is equivalent to delta omega, which also goes to 0. What you do is you replace a sum over the discrete frequencies n omega naught by the integral over all frequencies. Okay, so instead of adding up those frequencies, you integrate between them, and then you replace n omega by a general frequency variable called omega. And so you end up with this thing here. Okay, it's ugly. So that sum has been replaced by an integral. Okay, this is the same as what we had before, but instead of n omega naught, we've got just omega, essentially. And this term here is the Fourier transform of this term. So we represent that term, this one here, by big F omega, because it's a function in terms of omega. Because look, we integrate over for all frequencies, so we've got an omega in here, okay, this is a dt, and so f omega e to the minus j omega t d omega, okay. We've got a time domain function here and a frequency domain function here. This is the Fourier transform of this, okay. It's quite complicated, I know, and it's difficult to grasp on first sight. But read through the notes again, and hopefully it will become clearer. So f omega is this bit here, that's the Fourier transform of this, okay? And that's how you get it. Big F, which represents the frequency domain signal of omega, is this function, okay, which is an integral with respect to time, okay? And that's how we write it, okay? Big F of omega is this funny f, okay, which represents Fourier transform of f of t, okay? So if I had a function g of t, that would be big G omega, which would be this funny f g of t, okay, and so on. And the term f of t is called the inverse Fourier transform of big F omega, okay? And you can denote that by writing this means inverse Fourier transform. Take the inverse Fourier transform of something in terms of omega, you go back to the time domain. So this is that process I talked about. You've got your time domain signal, difficult to solve, you take the Fourier transform of it, so you do that first line, you get big F omega. That might be a problem that's easier to solve. You solve it, you then take the inverse Fourier transform of that, and you get back to f of t. So this bit is the frequency domain, because it's in terms of omega. So if you were to write this function out, you'd have a horizontal axis with omega in the bottom. Okay, and that's the Fourier transform of this time function. And then here we've got time domain. So you've got your horizontal axis with t on the bottom, and then that's what's inverse Fourier transform of the frequency domain will give you that solution. Time, frequency domain, time domain. Big F is frequency domain, little f is time domain. F omega is the frequency domain representation of the function. F of t is the time domain. And like I said, when you're dealing with capital letters, it's the frequency domain or the Fourier transform. And when you're dealing with the little letters, we'll talk about the time domain. And that's the convention I use. You'll probably remember back when you were doing control, okay, when you were doing Laplace transforms, you had a table of Laplace transforms from one form to the other, okay? And do you remember that? Yeah, when you had a transfer function, you separated it using partial fractions, okay? Separate it out into some set forms. You then looked up on the table of Laplace transforms to see what the time thing is. Well, there's a similar table that you can get for Fourier transforms, okay? The table's not in the notes, but that's because we probably don't need to use it. But what I'm going to do is I'm going to go through a series of particular functions to show you what the Fourier transform is, and we'll work it out analytically. And this is where you'll see that sinc function coming up for a rectangle. Okay, so that's what we're going to do now. Before we do that, I'll just introduce this thing called the Heaviside step function. Have you heard of that before? UT is simply for anything less than time equals 0, so anything on the left-hand side of a time line, we set the function to be 0. Okay? And for anything to the right-hand side of that t equals 0, you set it to 1. And that means that you've got this step. So if you multiply a function by that, the only bit that applies is the stuff on the right-hand side. Okay? Which can be appended to any function that applies to one side. So we've got a one-sided exponential. So here's our decaying exponential. Ut is our Heaviside step thing. And so if you were to draw it, you get this sort of thing. Ut, e to the minus alpha t on its own would start out at minus infinity and would come down, cross over at this point, and then keep on going. Okay? And if this is e to the minus t, that point would be 1. Okay? So do that. But obviously we've multiplied by this Heaviside step function, so this side of the graph, f of t is 0, and then from t equals 0 onwards we've got this function. So that's what that ut stands for. Where alpha is any positive constant. Okay? Positive is important because obviously you've got a minus times a minus, that becomes a positive, and you get a function that increases with time, not decaying with time. What is the Fourier transform of that? Well, here's the maths. Fourier transform in terms of omega, Fourier transform of this function, okay? And that's the equation for the Fourier transform. You stick in the function times by e to the minus j omega t, okay? Between 0 and infinity. Because it's only positive between 0 and infinity. We don't need to worry about the minus infinity to 0 bit, okay? Function times by e to the minus j omega t dt, okay? That's the Fourier transform equation. That's what it looked like. And that equation, if you were to look at it again, is on page it's equation 8.9 on page 128, okay? That's the equation there. This is relatively straightforward to solve. We've got an exponential, two exponentials. Obviously you can combine those powers in here, okay? And then you integrate. Well, we know how to integrate an exponential. It's quite nice and straightforward to integrate. You get this. You get the same thing, okay, divided by whatever's multiplied by t up here, which is that bit there. Between 0 and infinity, we stick infinity in for t. Anything to the e to the minus infinity is 1. Okay. No, it's not. It's, sorry. E to the minus infinity is 0. Okay. And then e to the minus 0, okay, is 1. So you get 1 over alpha plus j omega. Okay. E to the minus alpha t is 0 as t goes to infinity for alpha being greater than 0. alpha being positive. And you can note that this is a real, although the function is real, the Fourier transform is actually complex. There's a j in here. So it's quite difficult to draw on a real set of axes. What about rectangular pulse? Okay, so here we've got rectangular pulses are represented by the letter P, just a convention that you can follow. A represents half of the width of that rectangular pulse. Okay, so A. Okay, so the width of the whole thing is 2A. You've got A to the right and A to the left of t equals 0. And so that's analytically how it's written, and that's how you could draw it. Okay, so we've got time on the bottom, and you've got a rectangular pulse of height 1, okay, between minus A and A. Obviously, if you had 2 PA, then the height would be 2, and so on. Take the Fourier transform. So big P, A, okay, the Fourier transform. We integrate between minus A and A, because that's the only time when we're talking about a positive value. The value is 1, so we have e to the minus j omega t. Okay? We integrate that, you get minus j omega on the bottom between minus A and A. So you can stick in the values for minus A and A, and you get that. This is this term. E to the minus j omega A is cosine omega A minus j sine omega A. We saw that back in right at the beginning of this section. And you could write the same thing for this bit. Now we've got a cosine omega A minus a cosine omega A, so they disappear. And we've got a minus j sine omega A minus a j sine omega A. So we've got minus 2 j omega A, or sorry, j sine omega A. We've got a j on the bottom, j on the top. They cancel it out. We get a real function of sine omega A divided by omega. And note that in this case, the Fourier transform is real. Okay, so we can actually we'll be able to draw this on a real set of axes. Now, engineers often call the function sine of x over x. It's called the sinc function because it has a certain shape. It's called a sinc function. It's just the way we call it. And so if we write the transform in the rectangular pulse like this, okay, so we had sine of omega A over omega. If you multiply the top and the bottom by A, you get 2A sine omega A divided by omega A. And that sine omega A over omega A is the same as this sine x over x, which gives you sinc function in terms of omega A. So that's how it works. Sinc is like sine, but it's called sinc with a C at the end. And if you were to plot this, you get that. Okay? So for A equals 1, so that A disappears, you have sine of omega over omega, you get this sinc function, which is what we saw before. So the Fourier transform, P of omega, of a rectangular force, a step force that returns back to 0, gives you a sinc function. So there's an example. And like I said, this is what we saw that before. Okay, so the step force as the period goes to infinity, okay, you end up getting this sinc function as the frequency response of that system. What about a two-sided exponential? So this side we haven't got that heavy side thing. We've got a function that looks like this. Well, what you do is you deal with each half individual. Wherever you've got a discontinuity, like this point here, okay, you separate it out and you deal with each bit individually. Take the Fourier transform of both sides. So there's one bit, there's the other bit, and you go through. We've seen this bit before. Okay, that's what we saw for one side. The other side is exactly the same, except you've got a plus down here. And notice that we've got to get this out, we've got a j squared term, which disappears because the j squared is minus 1. You end up getting this term here. And so, for a two-sided exponential, you end up getting a real Fourier transform. depending on what A is.